If you work in tech, maybe you've heard the acronym PKI, or you've heard the term certificate before. In this video, we're going to demystify these concepts and see exactly why it's the foundation that secures the internet today. There's a little padlock at the top of your browser right now. If you click it, you will find a certificate. And this certificate is issued to a website. And it's issued by an organization that maybe you've never heard of, valid until a date a few weeks or a few months in the future. So what is this file and who is this organization? So your browser runs a check before it shows you anything on more than 95% of the pages that it loads. And it checks that there is a certificate and it's issued by a certain organization. Now, this is the reason that you can type a password into a website without it getting stolen. And it all sits behind a few important concepts. PKI, public key infrastructure, plus TLS and CAs. All of it exists to answer one question. When your computer talks to a machine that it's never met before, how does it know who that machine really is? Let's first start with what the world looks like without any of these things. When your browser loads a site over plain HTTP, the version without the S, everything that travels between you and the server is plain readable text. And this is going to pass through hardware that you do not control. So that's, coffee shop Wi-Fi, your ISP, a bunch of other unknown networks. And anyone on this path can read what you've sent. So this password that you type and the cookie that keeps you logged in are just sitting there in the open. And because every one of those networks isn't just seeing your data, but also passing it along, anything on that path could change what comes back to, rewriting a download link or injecting something into that page. Now that's the first problem. Someone in the middle, what we call a man in the middle, reading or rewriting your traffic. But there's a second problem. Say you fix that, now everything on the wire is unreadable to anyone in between. The second problem is that you still don't know who is on the other end. So if someone could trick your connection into landing on their server instead of your bank's server, unreadable traffic doesn't save you here. You'd be having this perfectly private conversation, but with a thief, thinking you were talking to someone else. So our secure connection needs two separate things. It needs encryption so that nobody in the middle can read or alter this traffic. And the second thing that we need is identity so that you know who's on the other end before you start saying anything secret. HTTPS solves both of these. It's just plain HTTP with a protective layer wrapped around it called TLS. And that's where the S comes from. TLS uses cryptography to scramble everything that you send so that nobody in the middle can read it or change it. And then proving who's on the other side is the certificate's job. So how does a server prove who it is to a browser that it's never talked to before over a wire that anyone can read? The answer to this problem is something called a key pair. A machine generates two keys at one time and they are a matched set. So one is a public key and it's built to be handed out to anybody who asks for it. And the other one is called the private key. So whoever generates it keeps it as the name would suggest and never sends it or shows it to anyone. Now these two are matched exactly. This private key goes with this public key and no other public key in the world. So they only work with each other. Now importantly here, they're not passwords for each other. So handing your public key away to a stranger gives them nothing because there's no practical way to work backwards from this public key to the private key. Now what this gets you is that this private key can produce a signature on a piece of data. Now anyone who's holding that corresponding public key can verify a couple of things. They can verify that the real key holder of this private key produced it, and they can also verify that the data has not been altered at all. Basically, nobody without this private key could fake the signature here. So a signature is a claim that only one specific machine could have made and that anyone in the world can check. This is what certificates are built on. So what exactly is a certificate? A certificate is a small file that ties a domain name to a public key. It's like an ID card for a server. The name on the card is the domain, say shop.example.com. The photo is this server's public key. And the hologram, this part that makes it hard to falsify, is a signature from the certificate's issuer, whoever vouched for it. Now, if I open up a real certificate, I can see that all of the fields that matter are right here. So I've got, for example, which domain name it covers, the server's public key, who issued it, the dates that it's valid for, and we've got the issuer's signature all over it. If I go to details, I can see the issuer and I can see this certificate hierarchy. And I can also see what this certificate is meant to be used for. Like here, it says www server authentication. So when your browser connects to a site, the server for that site presents its certificate. And then the browser checks it like a bouncer would a license. Does the name match the site that I asked for? Is it still within its valid dates? And is this hologram real? Is the signature from an issuer that I trust? Only then does it actually use the public key on that card to make sure that it's really talking to that server and set up this encrypted session and show you the padlock. Now this leaves us with a question. Who is an issuer that the browser trusts? So the issuer is called a certificate authority, or CA for short. Now a CA is a lot like a passport office. Your government runs one, and other countries accept your passport, not because they know you, but because they trust the office that issued the passport. And your browser and operating system ship with a list of CAs that they already trust, around 150 of them for the entire internet. Now, that list that we just saw isn't just a set of names. Every CA has its own key pair, the same as a server. And what ships inside of the browser is the CA's public key. So this is what makes that check possible. A CA signs a certificate with its private key, and your browser is already holding the corresponding public key that it needs to verify that signature. Now, one of these CAs is Let's Encrypt. Let's Encrypt is free, it's run by a nonprofit, and it signs certificates for a huge share of the public web. So when a CA on that list signs a certificate, every browser on Earth accepts it. And this is the entire trust model of the web, a short list of those passport offices baked into your software. Now, this also explains why signing your own certificate doesn't get you very far in this case. Nothing stops you from making one. This is called a self-signed certificate, but that's like printing your own ID at home. The name and the photo might be honest, but there's no hologram that anyone recognizes, and if browsers accepted homemade IDs, anyone could print one out that says, hey, I am your bank, and forge this signature and look like your bank. So your browser will show you this full-page warning instead. Real certificates have one more layer to them, and there's a good reason for that. A CA signs with its own private key, and that is the most dangerous thing that it owns. If the private key ever leaked, every certificate that CA had ever signed would be worthless at once. And there'd be no quick fix because the matching public key is sitting inside of billions of browsers and operating systems, and everyone would need an update to remove it. So CAs usually don't use that private key for daily work. Most of the time, they keep it offline, powered down in a vault, and then they bring it out for one job. And that job is signing a certificate for another key pair. Now, this second key pair does the day-to-day signing on a machine that's actually connected to the internet. Now, in this scenario, the offline one is called the root CA, and the working one is called an intermediate CA. Now, what this means is that a real certificate actually arrives as a chain. So if we take a look at what's happening here, in this case, we actually have 3 key pairs. Your server made a key pair, and the intermediate signed a certificate for its public key. The intermediate has a key pair of its own, and the root signed a certificate for that public key. And the root is what's sitting in your browser's built-in list. So we've done this same move twice now. Somebody with a private key vouching that a name and a public key belong together. And your browser actually walks that chain from the bottom up, checking one link at a time until it reaches this root that it already trusts. Now here's the thing. In this case, nobody signed the root. It actually signs itself. It's a self-signed certificate. Recall we had said that your browser rejects these. Well, the difference is that this root CA is already in your browser's trusted list. It's baked in ahead of time. And it doesn't need anyone above it to vouch for it because this chain of trust has to stop somewhere, and with a root CA, this is where it stops. So again, your browser checks each signature all the way up, and when the chain ends at a key that it already trusts, the whole thing holds up. So to recap, HTTPS is regular HTTP wrapped in TLS. TLS needs a certificate, and a certificate ties a domain name to a public key, and it counts because a certificate authority signed it. Your browser trusts this short built-in list of certificate authorities, and it walks the chain from the certificate in front of it up to one of them. This is PKI, and it isn't only a web thing. These same pieces show up anywhere that 2 machines need to be sure who they're talking to. Whether that's services inside of a Kubernetes cluster proving their identity to each other, devices on a factory network checking in. Maybe it's software signed so your laptop can tell where it came from. The browser is just where most people run into it first. And plenty of teams end up standing up a certificate authority of their own for those internal names that a public CA would never sign for. Now, there's one field on every certificate that we didn't touch, and it's a strange one. It's the expiry date. Certificates are built to stop working after a few weeks or a few months, and that period is getting shorter and shorter every year. So folks don't want to renew them by hand anymore. Why that is and what's doing the renewal is a whole subject of its own, so we'll cover that in a separate video. Thanks so much for following along. If you have any doubts about anything that we've covered in this video, let me know in the comments. I read every single one. We'll talk to you in the next one.